When a number passes before your eyes, what do you see? When Ferdinand Magellan made his famous first circumnavigation of the globe, his was the first foreign face ever seen by many of the native populations he encountered. It has been said that many natives did not even see his ship until they were close to shore, simply because those shapes were so foreign to them that they failed to register even as they looked directly into the sea. That boats could be so large, sail under the power of wind, and so far from shore were ideas they had never had to consider, so they simply didn't. They negatively hallucinated the ships. The ships appeared upon the horizon, but were not seen. When you look at a number, do you actually see it, or just a collection of symbols? Is there value in what you see? Can you see within this number? When the natives did finally see Magellan's ships, they had no idea what kind of armor, weapons, creatures would soon greet them, radically and forever impacting their lives. How might what's hidden inside a number impact your possibilities? What do you see, and how do you go about looking? Arguably the most important line ever uttered by Sherlock Holmes came in a scene from the 2009 movie where Dr. Watson is practically garroted by a razor-sharp glass cord, practically invisible to the naked eye.
How did you see that?
Because I was looking for it.
To help us with this, let me introduce our special guest, Mr. Sherlock Holmes. So, Mr. Holmes, what do you see in 3125?
It's obvious. I'm certain you can see all the pertinent details. Why don't you give it a go, and then I'll fill in anything you miss.
Oh, well, all right. It's 4 digits long, ends in 5, so it's divisible by 5. It is odd, so it's not divisible by 2. The digits add up to 11, so it's not a multiple of 3. Not divisible by 2 or 3, ends in 25. How did I do? Oh, wait, he's writing something down. $31.25. Ah, how does writing it down as money help us? Quarters. Every dollar contains 4 quarters. We don't know how many quarters it will break down into, but now we know it's divisible by 25. Imagine you're faced with the following problem and told to predict its product without doing any multiplication. Huh? Sounds counterintuitive, but that's exactly what I'd like you to try. So put away your calculators and pull out your deductive brains. Look deep into the number. 3, 1, 2, 5. 3, 1, 2, 5. 31.25. $3,125. $31.25. Now, what are you looking for? Well, how do 32 and 37 factor into the equation? We're being asked to find the answer without resort to multiplication, which suggests that our answer will be in some ways a familiar one. So Sherlock asks himself, which of the remaining factors might combine most nicely with 3,125? He quickly discards the 37. It's a prime number. It ends in 7, a number that doesn't multiply terribly predictably. How about 32? Ah, Sherlock is smiling. 32 is a very predictable number. Do you recognize it? 32 is 2 to the 5th power. 2 times 2 times 2 times 2 times 2. That's a lot of 2's. How might a bunch of 2's combine with 3,125? Sherlock? Oh, Sherlock is bowing out. Apparently this was enough to deduce the answer. What did he see? Did he start multiplying the 2's by 37? No, that's against the rules. But it's got me curious. Let's see. 37 times 2 is 74, times 2 is 148, times 2 is 296, times 2 is 592. I hope. No. If our answer is to be predictable, 37 does not appear to be the key. All right. Let's pretend we decided to play by the rules. No multiplication. It's time to take another look at 3125. What might we look for inside it? We've already seen that it ends in 5. How does 5 combine with 2? Well, multiplied, they make 10. Is that useful? Take a look at this. We know 3125 is divisible by 5. We just don't know how many times. We'll call the unknown x. And 5 times x equals 3,125. Since multiplication allows us to multiply in whatever order we choose, we can easily put 2 and 5 together to make 10. Does that help? I guess. We've got one less factor. It'd be nice to be able to repeat that process. Does that seem likely? Could we take out another 10? We've got plenty of 2's. We just need another 5. Remember our discussion of quarters. Every dollar has 4 quarters. So $31 must have a bunch of quarters in it. So 3,125 is divisible by 25. And 5 nickels make a quarter. We're whittling away at those 2's. This is beginning to look more manageable. Do you think we could be so lucky as to find another 5 in 3,125? Look at the last 3 digits. 125 or $1.25. Well, that's 5 quarters. Another 5. But what about the 3? Well, that's another $30. If you work a lot with the powers of 5, you know that all of them end in either 625 or 125. So 3,125 could be a power of 5. What if it was 5 to the 5th? Well, then we'd have a lot of 10s. And our answer would be 3,700,000. As it turns out, 3,125 is 5 to the 5th power. So our intuition was correct. But how did Sherlock know so early on in the process?
Oh, it was really quite elementary. The way the problem was originally stated left no doubt that the answer would demonstrate some recognizable pattern. The presence of multiples of 2 and 5 suggested a series of zeros. As 32 is 2 to the 5th power, it was immediately evident that a maximum of 5 zeros were possible, and therefore 3,125 would have to be 5 to the 5th. Therefore our answer was clearly 37 followed by 5 zeros. You say that is 3,700,000, and I will take your word for it. What that exactly amounts to does not interest me in the slightest. We were asked to write the number, and that is all. Task me to use that number, and I will take more interest. Thank you, Sherlock. I can't begin to tell you what a pleasure it is to have you on the show. Sherlock? Oh, he's leaving. Well, goodbye, Sherlock. Nice working with you. Anyway, thanks for joining us. This is Ron Bell saying, I hope you never look at a number the same again. Keep your eye out for another episode of Person-Centered Mathematics.